Here. Okay. that seems to bring us all to focus here. Recording in progress. Okay, so this is starting up a little slowly here, but let me start just with saying this morning's topic, data visualization, is one of my favorite. I really enjoy data visualization. I think everyone who works with data really enjoys data visualization. It's sort of the part, usually one of the last parts in a data processing pipeline is when you get to finally see what is in there, and that's really, really fun. And the goal of today's tutorial is to walk you through a sequence of ideas again and sort of broader picture, while also demonstrating code what I think is the right way to visualize data in Python. So we'll walk through a series of different libraries. You can think of this as a chronological or historical overview of data visualization in Python. I'm hoping this will work. But also as a kind of a set of theoretical ideas. While this is starting, I'll sort of give you a broad sense of where we're headed here. We'll start with Matplotlib, which is kind of the oldest and in some sense, most robust part of the visualization ecosystem in Python. And what it gives you is imperative control. It's called imperative control over visualization. That is, you tell Matplotlib, I want lines going from this point to that point on the canvas, or I want points in these positions on the canvas, by providing directly the data that you want to visualize, and that's called imperative. That's the imperative paradigm in visualization. In between, we'll stop a little bit to talk about something that's a little bit in between, that is statistical visualizations. So instead of imperative control, sometimes you want to do something that's a little bit more of a summary of the data that's provided and something that gives you information about the statistics of the data that you're looking at. So that's statistical visualization. And then on the far end of this continuum is something called declarative visualization, which is different from imperative in the sense that you now provide a whole data set and you say, you declare what the visualization that you'd like. You sort of describe the grammar of the thing that you'd like, rather than saying, I'd like these points to be over here. You say, I'd like to use a certain set of markings, and I'd like them to be in a particular way, and I'd like to compose the visualization out of these following kinds of elements. And I'd like you to figure out where to put the points, you being the software. I'd like the software to figure out where to put the points for me. So that's called declarative visualization, and that's on the other end. So then I'll show you a tool that does declarative visualization in Python, a really, really interesting tool, also from kind of like a theoretical point of view, because it comes from really interesting research in data visualization. And it's a tool that's quite useful and relates to things we talked about yesterday, because it's all about it interacts in interesting ways with things like tidy data and pandas and so on. So with that, and having now managed to get onto the, so we're here in the curriculum again. Where am I here? NH2022 curriculum. Rokem Viz is this morning. And I'm in this notebook. Let me just close everything because I don't know where I'm working anymore. There's other notebooks here, but this is the one that I want. And so let's start first with the fact that data visualization in Python can be a little bit confusing. And part of that is because there's so many different options for how to do it, right? There are these basic technical complementary to these theoretical ideas, these technical considerations. If you're working in the browser, and we are working in the browser right now, the natural language to use in the browser is not Python, it's actually JavaScript, which is the thing that the browser understands the best and works best with. And that's over there on the left. And so there's JavaScript itself. You could write JavaScript to put your markings in where you want, and there are great libraries for visualization in JavaScript. But let's say that you are working in Python. There is actually a whole ecosystem of tools that write you write Python and they write the JavaScript and they render it for you and do all kinds of cool things. On the other end here is Matplotlib, and Matplotlib precedes this whole web-based Jupyter thing by quite a few years. But there's a whole ecosystem around Matplotlib as well, and we'll see Matplotlib in just a second. And then in between, there are these things that kind of translate between them. There's a whole other ecosystem around OpenGL, which kind of like the high performance graphics of the graphics card itself. And there are Python libraries that work with that, and we won't look at that today. And then there are sort of these other things. So it's really confusing. There's lots of different things, lots of different options. It's also fun because there are a lot of different things and lots of different options, and you can experiment with them and find what works for you. A lot of people are working on this, among others, because it's really fun. Okay, let's talk about Matplotlib. So Matplotlib has been around for quite a while. It was started by a neuroscientist, John Hunter, who was at the time a postdoc at the University of Chicago and was working with electrophysiology data. It was working with ECOG kinds of things. These were pretty early days in ECOG, and he had the problem that he wanted to be able to visualize his data on multiple different computers, but he had to work with MATLAB, and so he had to kind of like figure out licensing, and he got annoyed with that, and he was quite technically adept. And so he wrote Matplotlib. And so Matplotlib was supposed to originally give you the look and feel of MATLAB plots with an API that resembles the MATLAB API. But it really took off since then. And, you know, it's become very central. John Hunter subsequently left academia and went to work at a hedge fund and continued to work on this. And over the years, Matplotlib really took off and was adopted by a lot of really high visibility projects. So this is the LIGO collaboration that detected the evidence of two black holes spinning around each other just a few years ago. And these are their visualizations all in Matplotlib. This is the famous image of the black hole that was created by the Event Horizon Telescope just a couple of years ago. So this is Matplotlib. This is Katie Bauman, who sort of led the team that did this. And so you can see Matplotlib on her desktop, which is cool, but you can also see the kind of feeling you get when you get a good visualization up with, you know, a groundbreaking discovery. Which, so I really like this photo, both for the fact that you see the Matplotlib window right here on her desktop, and also for the look of her on her face when she sees this image. And so it's really widely used. That's just to make the point. And I won't belabor it more than that. Yeah, and as I say here in the text, in other words, if you use Matplotlib, you're almost guaranteed to make groundbreaking discoveries. Matplotlib has a long history, and it shows in the way that the software is structured. It's got, like I said, it's got a whole API that is supposed to look like MATLAB, and you can write code that looks like MATLAB, and it behaves like MATLAB there. And that's kind of a weird thing to do because there are better ways to write code than writing in the way that MATLAB is structured. MATLAB, for example, is not naturally an object-oriented language. And so why would we not use the fact that Python is an object-oriented language? And so over the years, people have kind of cobbled on top of Matplotlib. It's very complicated. You write a software, lots of people use it, and now lots of people want you to, for example, maintain all the different APIs that the software has, because, I don't know, the example John Hunter used to give was that you would get like these emails from like the Mars rover team that is like, we have the Mars rover landing in 4 days and something in the new release doesn't work as expected, right? That's the kind of things he was facing. So it got a little out of hand, but there is actually, so as a new user to Matplotlib or even experienced user, you might look at this and say like, okay, so how do I use Matplotlib? And I'm going to present to you my opinion about how to use Matplotlib. What is the one true API? And it is this one, the PyPlot API. So when I use Matplotlib, my code will always have this line of code: import matplotlib.pyplot as PLT. That's the very beginning. And this is so Matplotlib is the library. PyPlot is kind of like a submodule And in fact, it's a submodule that exposes a particular API. And I've said the word API many times now, so I'll just explain what I mean by that. API is application programming interface. It's the way that a person writing software will activate the software, how you will access the functionality, what kind of code you will write. So this is a particular interface. And by interface, I don't mean the user interface, I mean the functions that are available to you, the objects that are available to you. And there are particular objects that are available to you here. But I'll go into more detail. There really is one true way to start any visualization, which is, that's maybe a little bit, putting it a little bit too strongly, but this is a very typical beginning to the code. Fig_ax equals plt.subplot. So inside of this plt submodule, there is one function called subplots that, confusingly enough, there's also one subplot without the S at the end, but this is the one I want to use, subplots. And what it does is it returns to you, it creates this set of objects. It's actually a set of objects on the screen here. And B, it gives you back two kinds of objects. The first is a figure object, and the second is an axes object. And the figure is, you can think of as the page on which things are drawn. And the axis object is the set of coordinates, is the canvas on which things will be drawn. And as I told you before, this is imperative. So I'm going to tell Matplotlib in my commands where I want to draw and what I want to draw on this canvas. So here's an example of that one method. So the axes, the figure exposes methods that pertain to the shape of this page and the ability to save this page into files and things of that sort. The axes object is this ax, the one I've returned as ax here, is the one that contains the methods for drawing things on the page. For example, here's a very simple thing we can do with these axes objects, which is to draw a sequence of numbers. So here I'm drawing a sequence of numbers. The default behavior here is to draw a line plot. This is inherited from MATLAB. Who here has used MATLAB? Okay, yeah, so you've seen this, right? You plot and it plots a line, and that's I think inherited from that, and is a reasonable default behavior. If only one sequence is provided, it assumes that it's uniformly sampled, then it will put it on the, it'll assume that the x-axis here is range number of points in the sequence. So you get 0 through 4 in this case for the 5 points that are in the sequence. But you can do things like this. You can provide 2 sequences, and then you get, how are things sampled? The first one is assumed to be the x coordinates. The second one is assumed to be the y coordinates, and or is in this command. So that's all very simple and straightforward. Let me actually pause here and see what questions you have before I move on into the next thing here. Great. Matplotlib precedes pandas by several years, but over the years it's actually developed the compatibility with pandas so that now Matplotlib can take pandas data structures and work with those. So here we're going to, is there anyone who's here now who was not here yesterday at the pandas tutorial? Okay, okay, there is one. Okay, so this is data we looked at yesterday, just to say, and so I'm not going to say much about it except that it's a real data, it's a real neuroimaging data set, and we're reading it here into a big data frame, which is this data structure that we saw, that most of you saw yesterday, but it's a big table in memory. I'll show you functionality, actually useful functionality of pandas that I didn't show yesterday. Let's say that we want to do something with this data. We played around with this data a lot yesterday, did some comparisons and looked at it on the screen. And I even showed you how you could visualize some of these properties directly through the data frame methods. But I think something that would be much more typical than the kind of explorations that I actually did yesterday is to start plotting stuff from this really quickly, get stuff on the screen, because a visual exploration of this data at this scale, 1,000 some rows, is going to be much easier by just looking at it. here's the functionality of pandas that I wanted to mention, which is that you can filter the columns. There's a method called filter, and you could give it a regular expression. So this regular expression will filter down to all of the area columns. There are area columns and there are the cortical thickness and so on. Here we're only looking at area, and we're only looking for the left hemisphere, and we're only looking for those marked as V, visual areas. And this 0 through 9 here says I want a number after this. So it'll give us only the visual areas on the left. So here is what let's say the mean across all the subjects looks like for all the visual areas that are part of the multimodal parcellation in HCP. So this, you can see how this can come in very handy. I've sort of filtered down the data based on the columns in this case, which is, this data is a little cumbersome because it's got all these columns, and that can be a little, if you want to do some analysis, this table is quite useful to you, right? We can read this out very quickly. But what we're going to do here next is we're going to try to visualize this. Yes.
Yeah, I had a really basic question that I could ask, and I can probably find online, but I've always been confused why sometimes people will do like back to this when you were plotting stuff like plot dot line plot, whatever it is, versus like axis dot plot or axis dot plot. Like,
okay, yeah.
Is there a reason that people choose one versus the other, or is it just?
Yeah, you're saying I could have written here PLT dot plot, right?
Yeah, or PLT dot, it's not like PLT dot line plot or something. That's what I always end up doing.
Line plot like this. Oh, okay.
Yeah.
Line plot is a Seaborn thing. We'll get to Seaborn.
Yeah.
But you could have done this, right? PLT dot plot.
Yeah.
And I'll warn you against doing that. It's the really quick thing to do. But the nice thing about having the axis object is that you can manipulate it. You can manipulate directly the thing. If you do PLT dot plot, there's an axis getting created. It's right there, but you can't do anything afterwards with it. It's not giving you as a variable. That's really the reason, to kind of get those objects and get control over those objects. You can add things here. You can set the X limits, set the Y limits, set labels, axes, and so on, which we haven't done yet, but we will do here next with this data that actually has meaning. So here is a more sort of typical visualization, and that actually demonstrates what I just said. Which is, we're going to pass this is a series object, but it's this series object. First of all, I'm creating a figure and an axis. Then I'm going to plot the mean area, the mean visual area left. I'm taking this series that I've derived from the data. I'm not looking at the raw data, I'm looking at summary of the data here, but we'll look at raw data in just a minute. And then, well, let's put this up, and I'll kind of go at why this code, A, what's cool about this code, and B, why it's written the way it is. So the final visualization here is a line plot that shows you the area, the mean area of different visual areas. And one of the things that is cool about this is that these tick labels down here, the labeling of the different points along the line, I never had to pass that. That came straight from the data frame, or from the series, I should say, not the data frame. I did, like I said, once I had the axis object, I could do things like, well, if I didn't do this, the reason I did this line here is that if I don't do that, then the labels are oriented, per default, they're oriented horizontally. But now I can go and say, oh, I want the tick parameters for the x-axis, the label rotation parameter to be rotate the label 90 degrees. And that went and rotated this so that it's more legible. And I can go and I can see, things that I might expect. The first few visual areas, V1, V2, V3 are very big. And then after that, things get pretty small as you go from there. So that's the thing that I might expect. And important to do, label your x-axis label or your y-axis appropriately. Yes.
That's a couple of spells for array filters to like get the visual.
Yeah.
Because it's much more effective than we've ever done this before. So the filter function is that really always going to work on columns, and then you do something like the loss to get for if you wanted to look across the rows, for instance. Like I'm thinking if you have rows that are like if indices, that are not numbers, and you're trying to like get whichever one, but maybe it was the indices were the actual areas. Would you just have to
Right, right.
a look function as opposed to filter?
So the joke I've heard is that, you know, I have a friend and he had a problem, and I recommended that he use regular expressions, and now he has two problems.
Yeah.
You can do a lot with regular expressions. I can't. You can do. I'm very bad at regular expressions, but I can write that regular expression. I guess I wrote that one here. But you can do a lot of filtering. This is I think it's very powerful, this idea. This is just one mode in which this filter function works. I'll show you another kind of filtering you can do. I think this works, right? Just FS, it'll find all the columns that start with FS and will give you those. I think you can even give it a sequence of the things that you'd like, but you can do that already by indexing, right? That's not, so this is a little bit also about the art of naming your columns, right? If you have a structure inherent in the columns, it's a good idea. Like whoever named these columns did a really good job. That's not me, but and kind of saying, oh, these are all these free surfer things. There are the area things, and then I have left hemisphere, right hemisphere. It's very clever. They named it very well.
But the filter is like part of like a pandas data frame, there's a filter function.
Yeah.
Okay.
This is a method from pandas, of pandas. This is the data frame, and this is the method of that. Yeah. Okay, so back to the visualization stuff. From now on, I hope everything will have X labels and Y labels, always have X labels and Y labels, so you know what you're visualizing. And this is how they're set. Notice that I've added here a little kind of neat thing is that you can write LaTeX into Matplotlib text, any kind of text that you're displaying by having dollars around it. And that's the reason that these units here of area are millimeter with the square, and this caret here raises the square up to a superscript because it's LaTeX. The things between the dollars are LaTeX. So that's a small thing, but kind of neat. Here I'm going to do the same operation and then do a slightly more elaborate visualization. Here, pretty quickly, this is getting a lot more complicated. Here I'm filtering for the right hemisphere visual areas. And now I've added another visualization here of the right hemisphere. And I'm attaching a label to each one of these lines to give this more, to give more information about what's going on here. I passed here the values. This thing here is a set of values. It is the array that stores the values. I passed the values rather than the whole thing, and that's I think because otherwise Matplotlib gets a little confused about the labeling down here, right? You still have left associated with every one of these because this first one came in with the left hemisphere labels, but they're ordered in the same way in both of those. And so that works. And so you can see Matplotlib adds another line here. And because I've labeled each one of these, when I call the legend method at the bottom here, it adds a legend. And it has some automatic way of putting the legend onto the canvas, and you can move it around if you need to, if it's blocking the data. It usually tries not to block the data. That's the main thing it tries to do. Let's get a little bit more elaborate here. In this case, you know, the continuous line gives you the sense that maybe there's some continuous data here, and that's not true. And so here we're customizing this visualization even more by defining the markers and the line style that will be used. So we're adding more and more stuff into the plot call. The plot call is actually a very versatile tool that has lots of options. In this case, we've added markers. This one is stars, this one is circles, and now it's a little bit clearer that these are not continuous data. You could make the line style. I think it's the string none. Here these are dashed lines, but I think none like that. Would then remove the lines. Maybe this is a little bit more legible. Becomes clear that maybe the only thing that really differs are maybe the primary and fourth visual area, something like that. So this is how I sort of start building a visualization that fits the data more and more. These are discontinuous data, so I don't want this to be a continuous line. If these were time series, maybe I would have the line there to indicate that these are data with some continuity. This is a little bit more about the style of visualization. Let me pause here. What questions do you have about so far about Matplotlib and how it works?
I think I missed when you were explaining like the mean area visual R dot values. Can you explain what that is again and like what it shows?
Yeah, sorry, I went through that quickly. So I did the same operation that I did up here to filter. Here, my regexes give me all the free surfer area in the left V with the number after it, which are the visual areas in the left hemisphere. That's because of this L. And here, I did the same thing, replacing this with the R, so it gives me the right hemisphere for the same corresponding. And so if I show you what that series is like, it's this series that has the same thing, but R's instead of L's here. Sorry, I went back.
Thank you.
So hopefully, if you've used Matplotlib before, hopefully this helps, and you've used it through some other kind of API. This helps clarify why I really like this API specifically, because you kind of start building things, and you can keep going with these axe methods quite a bit. You can go very far with those to control the visualization. And there are other ways to achieve the same goal. That's part of what's confusing about Matplotlib, but I really think this is a good way to go because you kind of start composing your visualizations this way. I'll show you one more kind of visualization here. Here the story is we noticed that the mean area of V1 in the right hemisphere seems a little bit higher. And so one way we could try to verify that is by plotting the scatter plot on an individual level. So here I'm extracting the column, the full series of the column of all the left V1 ROIs. And here I'm extracting all the right V1 ROI areas. And I'm scattering those against each other. And this would help me see if on an individual by individual basis, right hemisphere is larger than left hemisphere. And looking at this is helpful. You can try to sort of ballpark it, but maybe you can see already what's the problem with this visualization. Like, why is it hard to tell? I can't actually tell from this, is the right hemisphere consistently larger than the left hemisphere?
Axes are not whatever range.
Yeah, the axes don't span the same range. You can see that the lowest value on the Y is 1,000 and the lowest value on the X is 1,500, and the highest value is also not the same. So that, in some sense, the aspect ratio of this thing is not right.
Maybe you might also want to make it square as well.
Yeah, there's the rule in the kind of visualization theory is something called banking to 45 degrees. You want things like this to be roughly 45 degrees. And there's really the visualization for this kind of comparison. And also the one other thing to point out here is there's a lot of points here and they're overlapping. It's kind of hard to say. Are there just like 1,000 subjects in the middle and just a few in the ends, or what's the density of this thing? So we're gonna do three things here. We'll make the points a little transparent so that we can see how many points there are. The density of the ink will tell us how many points there are at every position. We'll add a plot of y equals x, which will really enforce or kind of tell us what is 45 degrees in this, or what is the equality. And we'll set the aspect ratio of the plot so that it's really square, and that looks like this. And this is, I think, my favorite kind of visualization in the world, really a scatter plot with the y equals x and two different variables on the x and y axis with this banking to 45 degrees, because it's pretty clear immediately that, yes, it's pretty consistent that the right V1 is larger than the left V1. But, there are exceptions to that rule. You can see them, who they are, who these exceptions are. This visualization is really useful. It's an individual by individual visualization. I can start asking what's wrong with these people, or what's right with these people. I don't know. What's up with these people over here, right? What's the difference between people that have very large V1s and people that have very small V1s? This is the start of a lot of questions. So it's a really useful visualization, and everything's labeled nicely. It's a thing of beauty, really. so going back to what the code does, there's the scatter plot here. I've added an alpha. The alpha is how transparent the point is, where 1 is fully opaque and 0 is completely transparent. 0.1 with this amount of data amounts to basically like a density map of the data. I've added the line from 950 to 5500 based on this first visualization. This is not something I could have known necessarily. I could have looked at the data and looked at the mins and the maxes and tried to guess that, but it's often an iterative procedure, visualization. You visualize this first and then you say, oh, look, it goes from 1000 to 5500. Let me start a little bit before and a little bit after. I've colored that black. I've added a dashed line style to that, then the labels, and then in the end, the aspect ratio is set to equal so that it's really square. And low, you have this thing. So that's nice. Let me stop here and see what questions you have at this point. Okay, a little bit more of visualization theory here. So I've mentioned a few ideas from visualization theory. Here's another one. Edward Tufte, who here has heard the name Edward Tufte? Let's see, just a very few of you, but you have heard. Edward Tufte wrote I guess he's some kind of political scientist, statistician, something like that. And he's still around, he's still alive, around and kicking, and he's still writing books at a ferocious pace. And he wrote a bunch of books about data visualization. The first one was really one that had a huge impact, was the visual display of, I forget the title, visual display of information, quantitative, here we go, here's his website. And here it is, all the visual display of quantitative information. I actually did remember the title, there you go, but there's a whole stack of them, and they're all great and they're beautiful, and they explain how things should be visualized. I really recommend, if you're into visualization, to get one of these from the library and or all of them and look through them. They're really beautiful. A lot of it is collections of visualizations that he's found and that he thinks are really great. So he points to all kinds of really cool visualizations and displays those. Anyway, one of the ideas that Edward Tufte introduced is the notion of what's called small multiples. The idea is this kind of comparison is powerful, but for a lot of data sets, including this data set, what we really want to do is we want to compare, say, V1 to V2 to V3 to V4, or this comes about in a lot of cases, like a lot of different countries to each other, a lot of different stocks to each other, a lot of different, you name it. In many cases, we have lots of units of measurement where we'd like to do the same kinds of comparisons across variables or display a variable. And he came up with this idea of small multiples. It's really a simple idea. It's the fact that if you have a good visualization, it becomes better when you add more of these. When you make multiple of these across different units of measurement, for example, different visual areas. And the way that that's instantiated in Matplotlib is through the subplots command. Again, the subplots command, we're going to use it. Before we called it with nothing in here, and that gives us one axes and one figure. If we start giving numbers in here, example 2 and 3, it starts creating small multiples, right? It creates multiple subplots. Each one of these on the page here is called a subplot. And the thing that we get back, this is why I printed the type of ax, is a NumPy ND array. So just to emphasize this again, ax itself is a NumPy array. So if I do something like that, it gives me the first row, the second column of this array of subplots. It's always two-dimensional because the page is two-dimensional, but it gives us sort of immediate access to individual subplots in this array of subplots because it is a NumPy array. That's a cleverness that was introduced into Matplotlib, that we already have a way to present arrays or to interact with arrays. Let's use it. And it has the shape 2 by 3 in this case, 2 rows, 3 columns, right? So the first argument here is the number of rows, the second argument is the number of columns. We still have just one figure here, which is the figure that contains all of these things. Okay, so now let's create a slightly more elaborate visualization. This is a lot more code. Here, we're going a few of the visual areas, V1, V2, V3, V4, V3A, and V3B. And we're going to use the same, for each one of these, we're going to extract X and Y are going to be the area of the left, the area of the right for each one of these visual areas. I'm using here a syntax in Python called the F string. If you put an F before the quotes, then any area of your string that is enclosed in curly brackets is going to be evaluated as Python code. In this case, the Python code is very simple. It's what is the value of this variable ROI, which is the variable we're going to go over here. But you can write more elaborate Python code in here. It will get evaluated into some value and then placed into that string. So that's called an F string. It's very useful, but it's used here primarily in order to pull out from this abide data the particular ROI that I have in mind here. I'm iterating not over ROIs, but over the axes. So I took the axes that I had, I flattened them to flat thing, and I'm iterating one over, going one by one over those areas. I've also started in kind of like an indicator variable here. I started at 0, and so when I come in here, it's 0 at the end, I'll increment it by 1, so I can go to the next area every time. And in between, the code here is, well, here I am actually automatically deriving the smallest and the largest to figure out the range of my my line, this 45-degree y equals x line. And the plotting code down here is the plotting code that we saw before for V1. Now I'm repeating that for every one of my ROIs. So this code automatically, in some sense, will create a visualization that has the small multiples display of these multiple areas. I've also, along the way, you can see that the labels also are also F strings with the ROI. So you get nice left V1 area, right V1 area, left V2 area, right V2 area. And here we are in the small multiples. You could argue that it would be maybe even better as a set of comparison, or as there's small multiples, if everyone had the same axes. And for many cases, I would actually recommend using the same axes. Like V1 is the largest, to use, 1,000 to 5,000 for everyone here. But in fact, because the differences are so big, you'd hardly see anything for this last one. So there's a trade-off there. But now again, you can kind of see lots of things. This is interesting relative to that one, right? There's an opposite trend here. This has a small trend maybe in one direction. This also has a small trend. You start seeing lots of patterns in the data. And this small multiple layout gives you a good comparison across different units of measurement and these variables. This contains a ton of information. It's already telling a scientific story, really, because about visual areas and their area across these individuals. We know that this group contains, there are actually two different groups here, people diagnosed with autism and not. You could color the points by that if you wanted and start making, we could start making scientific discoveries right here. By the end of today, we'd have the paper submitted. Okay, so that was a little bit more. So, okay, so this is a lot of code and I went through it really quickly. So let me just pause here and see what questions you have at this point. Okay. Anyone on Zoom have questions? I'm gonna just feel free to unmute yourself at any point and shout at me, because I'll hear the owls right in front of me. So I'll hear that. Yes.
Because we iterate through different regions, and we probably don't want to have the same values for V1 and V3. But is there a way to make it equal range? So the X and Y for each separate plot have equal range?
They are enforced here.
Yeah, but for example,
so you want everyone to have this 1,000 through 5,000, same as this one. You could. Yeah, we sort of pull out the minimum and maximum here. there's a little bit more to it actually, but because I look both at the X and the Y and I take the minimum among those minima in every point here. Or in every area here, but yeah, I mean, the rest is left as an exercise for the reader. One, to create this visualization. Try creating this visualization with the same. Take this code, edit it to create the same range for everything, and see what that looks like. Other things you could do here is: does it make sense to put all these points on the same axes? What would that look like? And then 3, I think an interesting one to combine with yesterday's pandas is: could we color each point by the group? I don't know, group by sex, maybe? So we get 4 colors. That would be interesting to see. I'm telling you, there's a scientific discovery to be made here. I don't think I've seen that before. I'm actually not kidding. I think there might be something in there. Okay. What other questions do you have? Okay, cool. So let's move on to statistical visualization. So I showed you this is really the imperative paradigm. I'm telling Matplotlib where to put the points, and I'm not deriving any kind of summary statistics here. The only summary statistic I did do was like average and display the averages. That was about it. But there's a whole set of people have come up with all kinds of ideas about how to display statistical information, and Matplotlib does have a little bit of that. Here's one kind of statistical visualization called the box plot. I'm never sure if it's called box because a person called box invented this, or it's called box because it's boxy. But be that as it may, it's a very common statistical visualization. You might have seen this before. Here I'm displaying, I think 1 and 2 is like, yeah, left and right V1. And I believe that the red here are the, help me here, people, view. I think that's the 50th percentile. This is
yeah, median 25th and 75th.
median 25th and median. So this is 25, 50, and 75 quartiles. This is 1.5 times the interquartile range up to this whisker, and these are considered outliers. All those that are actually displayed here as individual points are outliers because they're further than 1.5 times the interquartile range from I think the 75th percentile. So they're really outliers. So you want to really display them. There are all kinds of reasons to use this visualization. It gives you immediate comparison of the distributions, but at the same time, it tells you something about the outliershness of this data. So this is quite useful. One thing to notice here is it returns to you a dictionary, and you can start manipulating individual objects in here. So there are all kinds of objects in here that we haven't talked about, like lines, and you could do lots of things to manipulate this in detail, but we won't here at this point. And we'll see more statistical visualization in the next bit here. I'm just really quickly going to do a little diversion from the main thrust of this to point out that Matplotlib also visualizes images. This is useful in a lot of cases in neuroimaging data. Here I'm reading using NeuroHackademy, a file that's stored in the shared folder. It's the MNI template, the T1 weighted MNI template, asymmetrical. This gets the data from the file. NeuroHackademy has a tendency to lazy load. So here we're lazy loading the data, and here we're actually loading from file. Those of you who will come to tomorrow's parallel processing tutorial, this fact will become important then. And here I'm selecting from this anatomical image, on the last dimension, halfway through, and using Macho, which displays, so this is another method of the axes object, Macho, that shows a matrix of data and colorizes it in pseudo-color, with high values being bright yellow and low values being this blue. The default Matplotlib color map is really clever. I actually won't pause too much on this, except to recommend that you look up Viridis and a SciPy talk by Nathaniel Smith about this. It's designed according to human perceptual principles, very cleverly designed according to that. And there's a great talk. It's actually, if you're interested in color theory and so on, It's really a great talk about how to create a visualization tool that takes into account human perception. And this color map is great. That's all I'll say. But usually we're actually used to seeing this in gray. So here it is in gray. Gray is not too bad either. Okay, and just a few last thoughts here, since this went a little longer than I thought it should, but here we are, and I'll try to go quickly here after this. Is just to say the Matplotlib is huge, and there's a lot of examples in a gallery of examples in the Matplotlib documentation. And if you're thinking about a particular visualization that you'd like to do, and it's complicated, it's more complicated than what I showed, I would go here and just look at this and say, oh, what I want to do is a little bit like I want to customize the line style that I'm using, or I'd like to clip an image, or I'd like to, I don't know what, there's lots here. So look in this gallery and start with that code example and see how you go from there. So that's all about Matplotlib. What other questions do people have about Matplotlib at this point? Yes.
So there was this, one of these last parts where you showed this dictionary as the out. Yes, here. So I'm thinking back to our discussions yesterday, and would it be better if we turn this in using pandas turned into like
Good.
I'm not quite sure about the term, but into a pandas data set, so we can better work with the values of this dictionary.
Maybe maybe we could take that later because it's a little bit outside the scope of the visualization, but you can access all the details of this visualization, whether through this dictionary or pandas. I think Matplotlib would choose not to give you back a pandas because they don't want to rely on pandas, and dictionary is a native form. You can convert this into a pandas data frame if you'd like. So maybe that answers the question.
I had this understanding yesterday that it's like in most cases, maybe it's more useful to convert these dictionaries to like whatever dictionary we have to pandas or.
Yeah, so to dictionaries are very useful in many cases, but they're not the best form for tabular data. So you have to look at this and think, is this a table? Is this a tidy data table? If it is, then get it into pandas for analysis. If it's not, and it's not really, notice, for example, this means is actually doesn't have the same length as the other. So there's the others are the same length. So maybe, so anyway, that's okay. Just to say dictionaries definitely have their use, not as pandas tables. Yes, you have a question back there.
Yeah, I was wondering if there's any like Matplotlib limitations you warn against, or like any type of data it's not good to visualize.
Instead of answering that question directly, I'll go to the next step here, which is just to say, if you want to do statistical visualization and you want really pretty statistical visualizations and really effective statistical visualizations, Matplotlib, it would take you a long time to do this with Matplotlib. And also you would probably be replicating the work that Michael Wascombe has done in Seaborn. And so that's just to say, there are tools that are better suited for, and they build on top of Matplotlib, and Seaborn is built on top of Matplotlib, and are better suited for things like statistical visualization. I showed you that it can do a statistical visualization, but that's not the best tool for statistical visualization. Seaborn may very well be. So that's one kind of limitation. Yes.
It's also true to have interactions with the business. You play them, you know.
Yeah, so it's not interactive, right? It's hard to kind of like zoom in immediately, and I'll show a tool that lets you do that a lot better in just a little bit. Let me hurry up here because it's 9:50. Sorry about the hurrying up. I so enjoy talking about the really basic stuff, and then the ends of these tutorials end up being a little rushed. But here is the data again, and now I'm importing Seaborn as SNS. I should point out Michael Wascombe, who wrote Seaborn, did this as a way not to finish his PhD. Again, in neuroscience, he did finish his PhD, by the way, but it probably took longer than it should have because he wrote Seaborn along the way as a tool for his own research. Seaborn, who here has used Seaborn before? Lots of you. Seaborn does statistical visualization, and it takes as its native data format pandas data frames. So now we're really relying on pandas data frames and their properties. What Michael realized was that he had Matplotlib on one side, had pandas on the other, and if you could make those two talk to each other, you could create really great statistical visualization. He's also an extremely tasteful person, And so all the visualizations that he's created in Seaborn are very good looking. In contrast to Matplotlib, that can look a little clunky, like MATLAB. These are very pretty. So here I've taken and I've done that scatter plot from before. The differences are subtle, I'll admit it. I gave it as data, the abide, the entire table. I told it, put on the X this column, put on the Y this column, and I want an alpha of 0.3 here so that things look nice. And it goes and it does that. It didn't really bank to 45 degrees for me, but we'll do that next. But it did put the labels on here in a way that makes sense and so on. So this is pretty good. Here I can set the X limb and Y limb, and that banks it to 45 degrees. Oh, I should say here I've used Seaborn's scatter plot, which is a variant of the scatter from Matplotlib. It's very similar. You'll see that it looks very similar. Here instead, I'm using something called joint plot. This is already a lot more elaborate, right? It's got because I gave it the kind equals reg, which is a regression. It adds a regression line in here. This is not to be confused with the equality line. So I don't quite like this as much as I like the one that I showed you before, but this is pretty good too. It puts a regression line in there, which is useful in many of these cases. And it puts histograms of the marginal distributions of each one of these. And so you get kind of like the distribution for each, marginal distribution for each one. Here I've again banked to 45 degrees and set the aspect ratio by setting the X limb and the Y limb. And this code is pretty concise, right? I have a pandas data frame. I didn't need to do anything with this. I told as Seaborn which column to put on the X, which column to put on the Y, and add a regression line. It creates this quite pretty and useful visualization. Here's one more. Let's regex filter again here, and this gives me pandas data frame with only the V1s. And now I'm going to, so I have left V1, right V1, and I have different variables that characterize V1, right? So there are 4 variables here. I don't remember exactly what they are, but they're area and cortical thickness and a couple more there from Free Surfer. So we have quite a bit here. It's an 8x8 grid of these pair plots, right? This is 2 lines of code to create this pretty complicated thing. On the diagonal is the distribution of every one of the 8 variables that I have here. You'll see that each line has or each row has this straight line, and that's the variable compared to itself. But then you have scatter plots that are the pairwise comparisons of area to cortical thickness. Some of these, I'll admit, don't make sense, but imagine that you had a lot of variables and each one of these comparisons was sensible. This would be an interesting thing to do. You might say, well, maybe I want to, actually, this is not complete nonsense. We want to see if people that have large area also have relatively large thickness in V1. This one of these plots, although it's kind of hard because there are a lot of them here, will answer exactly that question for you. There's a pair plot. I'm actually going to skip over the next bit here, but there's a little bit more here in the notebook about exactly the variant of tidy data. We talked about tidy data yesterday. There's a variant called long format, and that's a little bit what Seaborn expects. And there's a little bit of pandas magic down here to get that to create, again, a box plot. Let me instead, so I'll leave that as an exercise for you all to look at later. Let me instead go to this last one, talk about declarative visualizations, because I just think it's a cool idea and something you might want to explore. Declarative visualizations is a lot more similar to Seaborn than it is to Matplotlib. Seaborn takes you part of the way towards, hey, I want a visualization. I want the X markings to be this column. Here's some data in a data frame. I want the X markings to be these markings. I want the Y markings to be these, and I want to add to it this following kind of thing. Altair, which is a Python library, goes really all the way to that, and I'll show you what that means in just a second here. I'll just mention that it's built on very solid visualization research foundations because it's built on top of something called Vega Lite that was developed by Jeff Heer's group here at the University of Washington. Jeff Heer is probably one of the leading if not the leading visualization researcher in computer science today. And so they developed this notion of declarative visualizations and how to encode them in a data format called VegaLite. And then Jake Vanderplas, who was my colleague here at eScience, developed on top of that a Python library in collaboration with Jeff's group to that is interesting, but to make that real in Python. And so here what I'm doing is I am creating a data frame that has the V1 information by filtering from a byte, and then I added subject, group, and age into that data frame from the original data frame. I filtered only for the columns here, the columns that have V1 in them, and then I've also added back the columns about subject, group, and age so that I can use those in my visualization. The way that Altair works is you give it this data frame, and you say, I want a chart out of this thing. So here I have a chart, and it has its data. No visualization yet. But then you can say, I want to encode X being this column, the area of V1 in the right, and Y to be this other column. So encode that for me and make that interactive. I have not done this. Before that, I said, I want to use a particular kind of marker. The marker will be a point. So the thing that activates the visualization is the marking that I have. And it puts on the page marking with points. It's interactive, zoomable, right? This actually some JavaScript happening behind the scenes to put this thing in there. So that answers the question from before. And I can do more complicated things. I can say, well, I want to encode these things, but I have other encodings here. I have color, I have size. So add, in color and size, add the age, and that encodes that. It gives us a nice legend here. Again, it's zoomable, pannable, and so on. So, I don't see anything systematic with age here. So there you have it. Also, once it's been created, you can tell Altair a little bit more about the nature of these variables. There are these conventions. For example, you say X, the group is nominal. I think N stands for nominal here. And then when you visualize it, it will say I have this nominal variable, right? So you can tell it something about the semantics of the data so that the encoding now is appropriate in terms of how the x-axis is interpreted here. This gets a lot more interesting when you start composing different transformations on the data into your chart. So here I have again, I'm doing this all in one here, which is kind of common for Altair. I give it the data, I say, give me a point marking, encode X and Y using these columns, and then take that chart and compose it with a regression transformation between these two variables marked as a line, right? And the addition composes these two kinds of things into now a plot that has a regression line on it. And as I say here, with these basic building blocks in hand, we do really cool things. I'll just mention here, if you go to the Altair website, that there are tons of really cool examples of these things. We'll just show one this one took a while to write. It's not a lot of code, but it took a while to write. And based on examples, so I really stole from Jake's examples, and to say, oh, we can also do something. There's this idea of selection. So they encoded into VegaLite, they encoded the idea that you might want to select some parts of the data. So there's a brush here that selects based on an interval. It resolves on the global level for the entire visualization. Here I'm doing, again, this marking. I give it the data, I mark things as points encoding Y age. Color will be this conditional on the brush, right, on this selection. Group as a nominal. And then if I don't select it, set it to gray. Add the selection, add the brush as a selection, and then set some properties here. And then this down here is a cool way of saying put two visualizations side by side, one of them encoding the area in right V1 and the other left V1. I probably should have put them the other way around, right? Yes, yeah, let me do that, because this makes no sense. The right on the left and the left on the right. There we go. Okay, so now we have the right on the right, the left on the left. And because I encoded this selection brush, I can brush and select certain parts of the visualization. And as you can see, selection, because it resolves globally, selection in one turns into selection on the other. And this makes, there's a lot of ways in which this kind of idea is useful. I won't belabor it too much. And you see, not a lot of code to create something that's really quite powerful. I think because it's interactive, it's no longer zoomable and no longer panable. It kind of says, well, you chose this kind of thing. I'm not going to give you this other thing, but I'm sure you could make it also do that. Notice this language is extremely limiting, right? You can't say I want points that are, you could probably set the properties of the points, but you can't say, hey, I want to put a point in X that position, Y that position. Entirely dependent on the data that was passed through all these transformations and so on. So you have a lot less imperative control, but boy, you have declarative power as a consequence of this syntax.
I have one question.
Yes.
How do you save this part?
How do you save it? You click on this thing here and you save as SVG or PNG, or you view. There's actually this is this visualization in the Vega Literal language. So there you have it. It's a big JSON blob. Yeah, there. These 2 points.
The automatic saving such that like you I don't know, you practice it.
Yeah, so you can automatically write this
Yeah,
into
instead of-
something. Yeah, I actually don't know off the top of my head, I'm ashamed to say. I'm not a heavy user of Altair myself, although there are people in my group who won't visualize anything else. To my embarrassment, I can't really do what they're doing. It's very cool.
So, would it be interactive still in one of those corners?
That's a good question. I think you can probably make that happen if you have the compiled Vega. There's probably a Vega viewer that will view it and still be interactive if you share with people. Yeah, and there are ways to create like dashboards in the Jupyter that will give you this thing. You can give somebody else the website they'll go to. It will be interactive. Yeah, so people who create interactive dashboards use these kinds of things to create user-facing dashboards. Okay, sorry, that was quickly through this idea, but I hope that gave you the idea that there's a range of different ways to visualize data. I think Matplotlib is still, for me, the tool of choice for like, I want to know exactly what my visualization looks like. But at the point where I start replicating, start doing statistical visualization, that's when I skip into Seaborn to do that. And then if I were doing a lot of these kinds of things and user-facing dashboards, this would definitely be worth the time to sort of dive into. I'll mention one more thing. There's one more notebook in here, since I know some of you, for example, hack projects next week will want to visualize brains. I just wanted to point out that NeLearn, which is a library that mostly focuses on machine learning in neuroimaging, and it's a great library for that, also has great visualization tools. And particularly if you're starting to think, oh, I want to visualize brains that are interactive in a Jupyter notebook, they have your starting point here in these very pretty visualizations. So just wanted to point that out without talking about it too much, but there's an example here in this fourth notebook. Okay, I think we're 5 minutes over, cutting into our longish coffee break, and there is something happening at 10:30. That'll be in the auditorium, I believe, all of us. So let's stop here and then take a break until 10:30 and see you on the other side of that.